let me figure out where, got it. There you go, Kahoot music. Hello everyone and welcome to lecture 12, I think. Is it 12? Yes, lecture 12. Where we're all about the linked list, the linked list. Now I'm your music, which is sorry in advance for that, because I'm completely tone deaf. Is the volume low or am I trying to speak lower? How's that? I was whispering so as not to interrupt the Kahoot music. I was also singing, so I was just saving you all from being subjected to that. We'll see how it goes after the Kahoot is off. It's louder because the input is from my computer. That's why it's louder. I planned for it that way. I forgot to start reading the names. Beautiful. Lots of cooked students. I hope not too cooked. I've got 4 weeks to go and then exam time. Ah, there you go. Someone's feeling confident. The goat. Someone's carbonating milk. Ew. All right. Should we get this party started? Oh, someone knows where it's at. I love COMP1511. That's right. That's funny. All right, let's do it. I'm good with weeks. It's week 7. Let's see who remembers things from yesterday. For those that maybe tuned in yesterday, a few people remember what to do from yesterday. Yay! So remember, you only compile .c files. You do not compile the .h because the .h is included in the .c files. And so when you compile the .c files, that means the .h is basically, you can think of it as it's copied to the top of your executable file, so it's all together for the machine readable. All right, so only .c files are being compiled. Let's see who's coming on top. Random guy, what a name. All right, random guy, doing well. Let's see if you can keep it up, keep up the momentum. What's happening here? Include, perfect, perfect, perfect. So remember, when it's your own file, you include it with the double quotation marks as though it's a joke, but it's not a joke, it's for reals. So only the standard C libraries are included with the less than and greater than symbols. All right, let's see next. Where have all the people gone? Indeed, They got, oh, random guy still on top. I'm impressed. Let's have a look. Yeah, week 7, this is where everyone drops off, and that's where things will get crazy. All right. Almost when you want to share function across files. Okay, so the reason it's not the other one is only if the project is large. But that's not the only reason to use multi-files. There are more reasons than that. What a tricky question. Tricked ya! That's not what the exam is like. Don't worry, the exam has no tricks in it. Let's see. Oh, random sky gone down. Sean has coming out on top, and salmon. And let's keep going. All right, now I'm just going to cook you a little bit in preparation for the lecture. Let's see what your strings are like so that I know what to revise in 2 weeks' time. Interesting. Very good. I forgot what the code was. I should have looked at the code. I can explain it for those when I look at the code. I was too busy, I don't know, dancing to the music. Jared is taking out the top spot now, and Salmon has moved to the bottom. I should have gone into sports commenting. I'm that good at commenting. Let's go. Next one. What is the output on line 6? Doesn't even make sense. It should be on line 8. Ooh. Oh, I can't just do that. How ingenious. Well, there we go. So what would be the output? You've got a string of size, so 10 A, B, C, D, E, which means all of it is filled. But when you have, say, string 3 is equal to string 5, remember that this is 0, 1, 2, 3, 4, and that means the 5th index is going to be a big fat null terminator, and that is why when you have into string 3 a null terminator, all you'll print out is A, B, C. Too quick, come on. I've got to keep you moving. That's why. We've got no time to waste. I'll make the next one slower. All right, random guys, come back. Sean's there. Salmon's there. Yo is in the building. What a name. Okay, question 6. When does the exam timetable come out? Absolutely no idea. I haven't even seen it. I think maybe it comes out tomorrow. I could be lying. I actually have no idea. The university would have, if you Google UNSW exam, provisional timetable for exam, it will give a date. Oh, I was talking so much I missed it. Okay, well we've got a string, and the string is pointers, and you're printing out, I should not have done this question at all. Good chat. You definitely did not have time to do this one. This was really just a guessing game. There you go. Bree has confirmed I am correct. The provisional exam timetable comes out tomorrow, and I am as excited as you about seeing it. Oh, he takes the lead again. Last question. This one is a 60-second answer. So take your time, but also don't take your time. I feel like this is also just a guessing game here, really. And the music now reminds me of when you get up to the castle stage. Here we go. The pressure's on. No. Should always be dogs, not cats. Random guy will not even receive any chocolate for this win if they do win. It was a guessing game, I can see right across the board. Beautiful bell curve, amazing. So the winner is number 3 is a smiley face. As my admins would tell me, maybe passive aggressive. Jared at number 2, and number 1 is it is Random Guy. What a comeback. Amazing. Amazing. Well done. Woo. Hope you're all ready for the rest of the lecture now. And I'm going to close this one. I'm going to leave that one. Beautiful. No, don't look at my, oh my God, don't look at my timetable. Don't look at my, no, I didn't mean to do that. There we go. I was just trying to get rid of, so that no one could see my desktop. Gets worse than this. And then it all gets put into one single folder. Here we go. We're back. I can go back and pretend like I have a very neat desktop. Okay. Hi everyone, welcome back. For those of you that were there yesterday, well done you. Hope everyone got their assignment in on time. I can see that some didn't, but maybe you've decided to take that extra day and lose that 5% off the ceiling. Perfectly reasonable thing to do, depending on, you know, making sure that you also get breaks. So just remember to eat, sleep, and exercise. Please remember to take breaks. Really important. So yesterday we started actually, I'll just check. Can everyone hear me fine now? Is it all right? It's a bit dark. Should I switch on another light? That did not do anything. Can everyone hear me? Yeah, all good. Okay, awesome. Okay, so yesterday we started to talk about, I just tripped over a chair. It's because I'm standing in my office and there's 3 chairs behind me. So yesterday we started talking about linked list, which is so exciting. Linked list is the best thing since sliced bread, so yay. And it's going to be, your next assignment is going to be based around linked lists. Sorry to even mention the word assignment. I know you're trying to recover on your 2 days of no assignments. But it's also going to be your second hurdle in the exam. So remember that the exam has 2 hurdles. The first hurdle is an arrays hurdle, which means you have to solve and pass a question with arrays. And then the second hurdle is a linked list hurdle, which means you have to solve and pass a question with linked lists. And those questions will be clearly marked in the exam, and you get 2 chances to do both. And it is just a pass. It's not, you don't have to get it completely right. You have to get half marks. Okay, and we will talk more about the exam later, so don't worry. The exam is, we will actually have a whole lecture to talk about the exam and to do some revision and to go over some questions, and you'll do a practice exam in your tutes and labs as well. Now, also, you might have noticed, and this is just a little bit of admin before we go to linked list, you might have noticed that there is just a lot of public holidays coming up. You've got all the Easter stuff, and then you've got the Anzac Day, so you've got there is a lot happening in that week 9, week 10. So we are going to, release extra tickets for classes because we do want you to come out and try the exam environment before you sit the exam, so you get a bit of practice with it. So those of you in online classes will get a chance to come in, and those of you that had a class that's either on a Monday or a Friday that you will miss, you will also get a chance to come into the labs and to actually log on to the exam environment and to make sure that everything works, so that we know that on the exam day we're going to have hopefully no problems. There have been some problems, but hopefully we will have no problems. Hopefully there will be no fires. We will be fine. Everything will be great. The exam will be great. You will all do great. I hope. Okay, linked lists. So if you remember from yesterday, linked lists is another data structure that allows us to solve problems. And basically a linked list has its pros and cons as well. So we know that with arrays, the memory space for arrays is contiguous. And we also have to say how big an array we want at the beginning. So when a program is compiled, that space will be allocated for that array, which means that if we ask for 1,000, an array of size 1,000, and we might use only 2 parts of it, well, we're wasting a lot of memory and a lot of space. So the program can become inefficient. So a linked list kind of combats that, because in a linked list, you dynamically allocate memory as you need it. So we make nodes as we need them. We don't have any extras hanging on, and we delete them when we don't need them anymore. So we are able to manage our memory resources much better. And whilst an arrays, you can go anywhere, any random index, you can access it by kind of saying which index of the array you want. You cannot do that in a linked list. A linked list is, you need the head of the list, and you need to travel to every single element of the linked list until you get to the one that you need. Because all that you know in a linked list is what comes next. So the node that comes next, that's the only node that you know, which means you have to start at the beginning, and then you keep kind of going towards the end. Okay, I see a lot of people are imagining sleeping. Just don't imagine that for the next few weeks. No, but please do sleep. Sleep is very important. Please don't show up to the exam and then fall asleep on the desk. I don't like that. It makes me feel sad. Okay, so how do we make a linked list? We make a linked list by defining a struct for a node, because we need to hold 2 different things in a node. We need to hold some data type. So we might have, we've just been working with ints, so we'll continue to do that for a little bit. So you might have an int data, and then what makes it a linked list is the fact that you have a pointer to the next node. So you will have a struct node pointer that will point to the next node in the linked list. So you basically have a little link chain, and you have to go to every link to kind of move along that chain. Okay. Someone noticed the cook tab. Thank you very much on the on our website. Yes, happy April Fools. It's not even, we're cooked. Everyone's cooked, and that is one of my favorite games, because you get to yell at people and there's no repercussions for that yelling. Okay. Anyway, tangent again. There we go. Okay. So a pointer to keep track of where to start of the list is. So we need that head pointer, and that head pointer is not a node in itself, but it keeps the address of the first node. And what it allows us is a way to know where that linked list starts. Okay, so we've got to have the head, which is telling us where the list starts. We've got to have a node, and then we have to have that next node, which points to the next node after that. Okay, so for example, this is let me move myself to the other side, because I'm not on a good side right now. Not for me personally, vanity wise, but for this linked list wise. Okay, so for example, a list with 1, 3, and 5. We've got a pointer to the head, and that is a pointer that points to the first node in the list. Then there is the 1 points to the next node, so it stores the address of the next node. And then there's 1 with 3, and it stores the address of the next node, which means it points to the next node. And the last node in the list will always point to null. And that's really important, because it allows us to know when the list is done. There is no other way for us to know that the list is done. So it's really important that we have that ability, because it allows us to traverse our linked list as well and know when it finishes, so that we know when we've reached the end. Okay, so we talked about moving through the list, and we do it with a while loop. But we also talked about the fact that we usually set our head pointer to a current pointer to keep track of where we're currently located. And the reasons we do that, sorry, I'm at uni, and for some reason there's sirens galore. I don't know what's happening today. So the reason, I hope everyone's okay, by the way, I don't know why the sirens. So the reason we do not modify the head pointer is basically what happens if I start moving the head pointer. I lose where the head was, which means I no longer know where the list starts, and I lose all the like kind of starting elements of all the nodes of the linked list. So I need to be able to keep track of where I am. So I always keep the head as the one that points to the first element, and that's why I create another pointer, and it's just basically a variable to keep track of, to then hold your linked list. So we start at the head or the current. The current is going to be over here at 1, and we then move along. To move along, what we do is we dereference current with the arrow. If you remember, that dereference is current. So if we're inside current and we dereference current, that means we travel to this node and we access the next. So the next is over here, 0xA44, and then we assign it to our current variable. So it gets the new address of the following one, which means that with this command, you're moving your current along to the next node. So current is equal to current next. It's what shifts us along to the next node. And don't worry, we will go through the code and we'll play around with it as well. And so I move it along again, so I'll move it along again. So, and then you stop by knowing that you've reached the null pointer. Now there's going to be cases, and we'll talk about them in the next few days, this week and next week, where you might need to stop at the second last node, or there might be the case where you go through the whole list and stop at the null pointer, but not access it, all right? Very dangerous to access a null pointer. It's something we do not want to do because you're trying to access some memory that doesn't exist, okay? You go into the void, the black hole of memory. Absolutely, we do not want to do that. Okay, so the only way that we make our way through a linked list is like a scavenger hunt when you used to do as kids, which means that you follow the links from node to node. You only know what the next one is. You can't skip nodes. You just go from one to the other. So that means we have to know where to start. We need to know the head of the list. And then when we reach the null, that means we have finished. We've reached the end. Okay, so we have been inserting, yesterday we were inserting at the head of the list, which means that we constantly stuck a node in at the top, and then just moved the head along to make it the subsequent nodes of the list. So today we're going to look at inserting anywhere in the linked list, okay? So where can you insert in a linked list? So the thing with linked lists is you really need to draw them to see what are the edge cases and what are the things that can go wrong or can't go wrong. Where will this stuff me up? Everywhere, really. That's always the answer. So it will cook you any which way. But I think linked lists are easier because of that. So you can insert in the linked list at the head, which means that you have to, what we just did yesterday. You can insert into the middle. And I'm using yesterday's lecture notes, which is why it says next lecture, but it's actually today's lecture. So if I insert into the middle of two nodes, that means I now need to hook the next to the new node and the new node to the one that was next before, okay? And it really helps to have a diagram because you can really see who you need to hook up to, which one, and where do you need to make the connections. Otherwise, if you just do it all in your head, you start kind of losing the plot a little bit and you make mistakes and the links will be all wrong. Okay. And then of course you might insert at the tail end of things, which means you'll just have to hook up the last node to the new node, and then the new node has to be going to null. So let's try and insert a node anywhere. How does that sound? Look, I've prepared myself with a whiteboard and everything. I don't really know where to put my camera still, but I will move it as we go. Okay, how is everyone feeling so far? Like theoretically, do you understand? I'll do it in a poll. So theoretically, do you understand what a linked list is? No, I'm going to be sad now. Someone doesn't understand what a linked list is. All right, let's see if we can clear up any misunderstandings of what a linked list is today. And then we can do this again at the end, this poll. Okay, so would it help if I ran through the code that we wrote yesterday again? Oh, this should have been another poll. Just, do you want me to run through the code again that we did yesterday? Come on, feedback. I need a loop. Yes. Okay, let's do it. Basically, it's like taping film rolls to each other. Kind of. It's an interesting analogy. I don't mind it. Okay, so yesterday we did something that made us build a new list. Okay. Yeah, I'm worried that film rolls is a very old thing. So, well, it's not an old thing. I used film rolls, which means they're a young thing. But no one uses them anymore, so perhaps not. Okay. So yesterday we made a function called create node. Okay, so what I'll do today, before I do that, what I'll do is I'm just going to show you, even though we did this code yesterday, what I'm going to do actually, I've decided right now, is I'm going to do for you just in the main how I would create a node to start with, and then I'll comment it out to make it, to show that it just goes to a function. So if you want to create a node, okay, so to create a node, you want some memory. To create a node, I need some memory to place this node into. So what I do is I use the malloc command, and I want to create a node. So that means that I'm requesting like a spelling fairy to come and make me spell things better. So basically, I'm requesting some memory, and the size of that memory is going to be the size of a node, okay? I want there to be enough memory to hold a struct. And the reason for that is because a struct holds in it some data, but it also holds in it a pointer. So the amount of space has to be able to fit all of that in. So I request enough memory to fit a node because that's what I really want. And so when I malloc some space, the command malloc, well, not the command, the function malloc, what it does is it allocates memory. That's why it's called malloc. And it returns to us where it has allocated that memory. And the reason for that is because on the heap, let's say that this is my heap, which is another part of memory. Well, this is not helpful, is it? Okay, so on the heap, you don't have to have sequential assignment, right? I'm not just going to assign from left to right, okay? This is memory, then the next bit goes here, then the next bit goes here, then the next bit goes here. It doesn't work like that here, right? On the heap, I assign memory wherever I see a little chunk that can fit in. So I could assign my first bit there, my first chunk of memory, my second one here, my third one can go here, my fourth one over there, and so on and so forth, right? And the chunks might be different sizes because I request memory for different things. So that means that when I allocate that memory, I need to return where on earth I've put this little chunk of memory, because otherwise I've got no idea where it is, right? It's not sequential. There's nothing to tell me where is it. So basically it is saying this is where I've given you this memory, okay? So good luck, enjoy that. So because this is the first node that I'm creating, I'm going to put it into a struct node head. So what that is saying is that I have a pointer called head, okay? And that pointer is just a variable type that is going to hold an address, okay? And that address is going to point to a struct node because I have allocated memory for a struct node, which means that the memory piece is holding a struct node. So this head is now holding whichever piece of memory on this heap that I've created, okay? So let's say it was this piece over here. I've created this I've called up memory. I said size of struct node, which means that it's created a node for me with two things in it. And inside head, I'm holding the address of that memory, okay? So malloc returns a pointer. It returns a pointer. It returns the address of the memory that it's created so that you know where to find it. Great. What that means now is that I have an empty node, okay? There is nothing in it, okay? So what I do next is I initialize that node. It means that I assign some values to it, right? So I assign values. A node has two things in it. It might have more things in it. In our context right now, our simple node has two things in it. It has an int data, so I have to initialize my data, and I have to initialize the pointer next because my struct node has a pointer to the next node. Okay, so to initialize the data to access a struct pointer in a nice way where I don't have to dereference it. So this memory is now stored inside the head, okay, which means that I would say, okay, head data. So what this does, this arrow here, is it says dereference head, which means, okay, the address, go to the address that is in head, which means go to this node and access the data element of it. So I access the data member of it, and I can now assign a value to it. So let's say I assign the value 7 to it just for funsies, okay? I just made that up. The 7's made up. Great. That means I've now taken care of this part of the node. I now need to initialize the next part, which is my next pointer. Now, there is no other nodes in this list. It is one node. It's on its own, which means that I'm going to dereference head again, and this time I'm going to dereference the pointer next, and I need to place an address in it, okay? The address of the next node. I don't have a next node, which means that it's going to be null, okay? Null means there is nothing there. It is null, void, there's nothing happening, okay? It means there is nothing in there. Okay, so what this does, these 3 lines of code, is it mallocs some memory on the heap. It then assigns the value 7 into the data, and it assigns the value null into the node. And the way I know how to find this node is the address is still sitting in head, okay? So if I were to then create another node, okay, and if I weren't using functions, if I was doing it sort of the really slow way, and this is not, do not do it the slow way, you will need to use functions, I would need to kind of go again, okay? So I would have my next node, head 2, and I'd malloc some memory for it. And I'd take that memory, and again, I want the memory to be a struct node type, and then I would do the same thing. I'll have head 2 for the data, I don't know, let's assign it the value 5, and head 2 and next is going to be null. Okay, for example, okay, so let's see what this does. What this does, again, these 3 lines of code, it goes through and it creates another node, that malloc. It creates an empty node and it stores the address in a variable head 2. It then on line 38 assigns the value 5 to it, and it gives this one as null. Now, exactly, we want to connect the nodes, right? Because otherwise we just have 2 nodes, they're sitting separately, it doesn't make any sense, right? So we want to connect them together. So I want my list to be, I don't know, which way should we go? let's go from this head 2 to head, okay? So I want to set the address of head 2 to point to this one, okay? So I want the list to go 5 and then 7. So that means if I want this second node over here to point to this list, my next is going to point to the value of head. Yeah? So what that means now is my list looks like this. The list right now is 5, 7, and then I have null. How is that feeling? Is that feeling good? I've got this poll running. If I do it the other way, what I could then do, okay, I'd keep this as null, and it's only because we haven't quite worked out which way to go. But I could say, if I want to go from 7 to 5, I could just go head, next, not like that, is equal to head 2. Yeah, and that means that head next is now going to have the address of head 2, so it will go this way now, and this will still be null. Okay, how are we feeling? All right, so you can see that this over here is quite repetitive, right? I'm not going to keep doing this again and again and again. It's insane to keep doing it again and again and again. What I'm going to do is I'm going to create a function that does it for us. And this create node function is doing exactly that. It's doing those 3 lines of code. It's mallocing some memory. So it's grabbing a piece of memory, it's putting it inside this new node, and it's assigning it whatever data was sent and whatever the next node was sent. Okay, so it's just allowing me to initialize the node, and then it's returning the address of this new node that was created. So these 3 lines of code here are doing exactly what we're doing inside the function here. Yeah, how's that? Let's poll that, start a poll. Yeah, look, I tried to teach some non-malloc in the course 1 year ago, and I regretted that life decision, and we shall not do it again in 1511. Okay. All right. Oh God, it got worse after my explanation. That is not what I wanted to know. So I'm going to comment this out because we've moved this into a function. Okay, so I'll just, again, this code is not going to be off. This is not going to be nice code. So the reason the create node is working like this right now is because we haven't got to inserting anywhere. So we're about to change, it's about to get fixed up, right? So create node was just inserting at the head each time. So the list was going to be the opposite, right? 751, it's the opposite way. Generally you add wherever it is you're asked to add, and wherever the problem kind of asks you to add. So different problems rely on different solutions, and you might need to add at different places off the linked list, and it's not necessarily always at the head, but the head is considered to be so always when you're testing your linked lists, if you are inserting nodes or deleting nodes, let's just focus on inserting, you will always want to be able to check that inserting at the head works, inserting at the tail works, inserting in the middle works. Okay, those are just the 3 basic things, and then depending what the problem is, you might have other edge cases. Okay, So we've got a function to create a node, which allows us to create nodes, and we've got a function to print the list, okay, which just traverses the nodes until they get to the last one. So until when we exit this while loop, and I always think this is something that's obvious but not obvious all at the same time, but when we exit this while loop, current is equal to null, okay? It means that I've gone beyond the last node of the list and I'm standing right past it, you know, in the void. Okay, so this allows us just to print the list. So if we just, to refresh, if we go through and we if we run this piece of code just to refresh your memory, what it does, so linked, what's it called, list.c. Okay, so it's just printing out 751. We've gone to the end of the list, okay? Okay, we're going to insert anywhere. Is it possible to traverse the linked list in both directions? What a fantastic question. It is possible to do it, but not in this single linked list that you are learning about in 1511, okay? And the reason for that is we're doing only one way, okay? You're only going forward always from start to finish, and that's it. So a double linked list can have a previous and a current pointer. So you'll have 2 pointers in your struct node, and they will have the ability to go backwards by 1 as well, okay? But you're not doing them in 1511, okay? You're just going one way, single, and you're going in one direction, forward. Always forward. We always move forward. Okay, so now let's do insert at the tail. Let's insert at the end of the linked list, and then we will insert anywhere after the break. So let's do insert at the tail. Okay, so let's have a function that inserts at the tail of the list. What do we think will be the input into this function? And what do we think will be the output of the function? What do we reckon? Yeah, so we give it the list that we want to get through. So we need to give it the head of the list that we are moving. We also need to give it the node that we want to insert, yeah? And the output is going to be the head of the list. Well done, okay? Okay, so that means that we're going to look something like this. Struct node and a really insert tail. And we're going to give it, what are we going to give it? Are we going to give it, should we create it in here? Yeah, I'm just going to go int data. I'm going to structure it like this. I'm not going to give it a whole node. I'm just going to give it int data, and then I'm going to give it the head of the list. Okay, fantastic. So we're getting to it. We will be adding to we want to edit an existing node. We will do that. Don't worry. It's coming. It's coming. You're jumping ahead. Let's just insert some nodes first to see how it works, and then we will. But those are very good questions. You can definitely do all of that stuff. Okay. We want to, first of all, create this node, right? So I've given some data, and I know that I want to insert this at the end of the list. So the first thing that I'm going to do is I'm going to create this node that I'm going to insert. So I'm going to create a pointer, and I'm going to malloc some space for this node, and I'm going to ask for a struct node size of space, and then I'm going to return a pointer called new, and store it in a variable called new node, the pointer to that memory that I've just allocated. And what I'm going to do is, you know what, why am I doing this? I can just use my function. How silly. let's use our function. Why would we waste time doing this? That's why we have our function. We would create the node and we would give it, I'm obsessed with the number 7. We would give it this data and we would give it null. So what this will do over here is it will return the address of a new node with data and null. So it's not pointing anywhere. It's still just an empty node. Yeah? Okay, next thing that we want to do. What is the next thing that we want to do? We want to loop until we get to the end of the list, don't we? So you're going to get very used to doing this. Struct node current is equal to head. What I've done here is I've taken whatever is sent to me over here, so the address of the head of the list, and I've put the address into a new variable called current, so that I don't modify the head of the list. I still know where the head of the list is. Okay, so I'm using current to move directions. Okay, so now if we have a look, we have a list with 751. So I'm going to draw it. How will I do it? Yes, I'm just going to do that, and I'm going to do that here as well. So right now, this is what we look like. 7, 5, 1. You can't see me. And null. So this is what I look like right now. 7, 5, 1, null. Let's say I want to insert, let's say this data is going to be, I don't know, number 11. Who cares? It can be anything, right? That's just pulled out of thin air. Okay, so when I go to this line here, what I've done is I've created this node. So I've got this node, and this node has the number 11, and right now it's pointing to null. So right now, this new node is pointing to null. So what I want to be doing is I want to insert it as the tail of the list, which means that I want to insert it. I want this last node right now to actually point to this and not to null. So that means I want to access whatever the next is here, which right now is null, and I want to assign it whatever address that this new node has, okay? The rest of the list stays as it is. So if I were just considering this list that I have in front of me without thinking of any of the edges that we might have, which we'll talk about in a second, and we'll see if everything works, how would we loop through to get to the end of the list? What do you guys reckon? How would we loop through to get to the end of the list? What do we reckon? Is it frozen? Has everyone lost me? Okay, so everyone's saying whilst current is not equal to null. Okay, we'll talk about this in a second. Hang on. Okay. While current is not equals to null. So remember, that means that when I exit this, while current, I'm going to move my thing along. So current is equal to current next. Okay. So what this means is that when I exit this while loop, yeah, my current is going to be equal to null, which means that I'm going to be standing over here, okay? I'm going to be standing at null, and I've lost this last node. I don't know where it is to be able to modify it. I've gone past it, okay? So what that means I want to do is I actually want to stop at this node over here. I want to stop just before it gets to null, okay? So I want to stop my movement when current next is equal to null. So when I use this syntax, current next is equal to null, what it means is I stop at this node over here because current next of this node is equal to null. So I'm stopping at the node that says my next one is null, and that means I'm stopping at the last node. So in this case, I will loop through until current next is not equal to null. So at this point, that means I am now standing at the very last node. Okay, great. I'm standing at the very last node, and what I want to do now is, instead of having this next is equal to null, what I want to do now, right now it's null, but what I want to do now is instead point it to this new node that I've created. And the new node is stored inside the variable new node. So that new node is over here. Okay, so to connect them up, I'm just going to do current next, which means dereference the current node and go to the next member of it. And then instead of it being null, I'm going to allocate the address of the new node to it. So I'm going to allocate new node to it. Now, the reason I don't need any asterisks here is because this is something that holds an address and this is something that holds an address, okay? If I now use an asterisk, it is such a complex word to say. If I now want to use an asterisk here, what I'm saying, I want to dereference this. This means go to the address in this node, okay? So I actually just want the variable itself, the pointer, because it's holding an address. And as we said before, we return the head of the list. Yeah, so because that's where I'm starting, but now it's hooked up to a new element. Okay, let's see if we can use this function and then we can go over it and execute it as though we are the computer. Okay, so let's add it here. And let's also this time call it, so I'm going to print it without, and I'm going to call this function, and I'm number 11 and the head of the list. And then I'm going to print the list again. So I'm going to call the function to print the list again. Okay. Let's try it out. Oh, I'm pleased to see that I'm not the only one that struggles with asterisk. It's too many S's. Who came up with that word? Okay, compile, success, and let's run it. So if we're to have a look at it, the first instance of the list is 751, which is what it was. And the second one, when we added our new node at the tail, is 75111. Yeah, does that sound good? How is everyone feeling? I'm not very good at doing these polls. Okay. Should we run through the code and execute it as though we're the computer? It feels like there's a delay. Okay, let's do it. Yeah, okay. Sounds good. Let's do it. So we've got this function, insert tail. I'm going to just pop that down. And up here, just so that we don't have to go, I've called this function, and I'm going to just move the call into a comment here, just so that we can see where everything is at. Okay, so I've called it with that, which means that I've called this function, and my int data is 11, and my struct node head is this head thing here. Okay, so I've called it with two things. Okay, fantastic. So what happens now? Let's have a look. I'm going to, let's just move this up. No, I want to like have it, but also not have it. I want to be able to have the code. I want everything. Great. Okay, we've called our function with insert tail. We've given it 11 head. Line 87, struct node new node. Let me delete this. Line 87, struct node, new node, create node. Okay, so I go on the right side first. It means I am calling a create node function. So I'm now going to call this create node function, and I'm going to give it the data. So this data over here is going to go down, so 11, and then it's giving it null. Okay, so it'll go up to the function that we did before, this create node function. And it will say, okay, new node is equal to malloc size of struct node. So that first line is going to malloc some space for us. So it's going to allocate some memory off a struct node size. And then what it's going to do is it's going to place the address of this new node into the variable pointer new node. Okay. Then I'm going to dereference this new node. So I'm going to dereference whatever is sitting inside this new node. Go into the node, the address of the node, go into the data element, and I'm going to assign the value of data to it, which was 11. I'm going to assign 11 to it. And then I'm going to do the same for my other member of the struct. So I'm going to go dereference the new node. I'm going to go into the next struct and assign to it whatever was sent to it with the next, which was the other thing I sent it, which was this null. And then what I'm going to do is I'm going to return the new node. I'm going to return the address of this node. So over here where it was called, I'm now returning the address of the new node. It's called the same, but remember they're not the same variable. But what happened is my new node is now has the address of this node that I've created. Excellent. The next thing I do is I take the head of the list, which is sitting over here. So it's pointing to this number 7 over here. And I assign that value to a variable current. So remember, head just holds the address, and now current is also holding the same address. So current is now over here as well. Great. I now enter my loop. Current next, dereference the current pointer, see what's next, and check if it's null. Is it null in here? No, it's not, because I can see that it's pointing to a node. Okay, great. It's not equal to null, which means that this is true. So what I'm going to do is I'm going to go into this while loop, and I'm going to increase the value of current. So current is now going to be assigned the value of current next. So whatever's sitting in here, I'm going to follow it along, and now my current has moved over 1 to the next node. I'm going to check again. Is current next equal to null? So is this in here equal to null? No, it's not, because I can see that I've got one more node sitting here. So it's pointing to something, not null, which means that I'm going to go again. So I'm going to increase again. So my current is going to migrate over to the next node. Whatever is sitting inside here, that's where it's migrating to. So the current is now sitting over here. Great. And I go again in the loop. I'm going to check, is current next equal to null? So I'm going to go in here and I'm checking, is it equal to null? Yes, it is. It is equal to null because I've got my null next. There's no more nodes left. So that means I am not doing this and I'm moving outside of this while loop. So I'm exiting the loop, and that means I am now sitting on the last node. So I am over here on this current node. And what I'm doing now is I'm saying, okay, the address that is stored in the new node, so this address over here, assign it to whatever is inside current next instead. So current next, which is over here, is now going to have the address of the new node. And this new node obviously leads to null as well. Okay, so good question over there. How come we didn't use this? That's because this is a dereference pointer, which means go to the address in that pointer. Whereas what we're doing is we are just changing the actual address in the pointer. So these are both pointers right now, and these both hold addresses. And that's why they can be assigned to each other. If I dereference this, this is no longer an address, okay? This is now what is stored at that address. I hope that makes sense for that question. Why do we need to return head and insert tail? What a fantastic question. Do you reckon you can think about, oh, Bree, you answered it too fast. You should have given it 1 minute. I was about to say, oh, what do you think? What happens if you have an empty linked list, you're inserting at the tail, and that is the only node that you've made, okay? I mean, we're fantastic. We've got 3 elements in, but if we didn't have any of this, we'd only make 1 element and it would be the head, right? the head would be null. So that's why we always return the head, because in a linked list, you always consider those few cases that are considered, edges. What happens if it happens at the head? What happens if it happens at the tail? What happens if it's an empty list? What happens if the value is not in the list? And then you just check what happens if, if you're doing exactly what you want to be doing is. Okay, so I think we're going to, now is a very good time to take a break, and then I'm going to have a drink, I'm going to practice saying asterisk, and then when we come back, we're going to insert anywhere in the list, and we're going to try to insert into, we'll do some more kind of, maybe no edges today, not too many, because let's just get it going with a very basic case before we do that. And what I'll do is, whilst we're having this break, I'm going to run a poll to see how we're all doing, so that I know how to pace the next lot of lecture. Okay, let's have a little break. So I only have a lecture will begin shortly, which is just a really rubbish thing to give you. Oh, I do have a little, let me give you a little something. Just realized that I'm also on mute. Thank you very much. Yep, thanks. Good chat. Good chat. I was just telling you I sculled like 3 glasses of water, which I never do. I am the most dehydrated person alive. Where's random guy? Doesn't want to be toppled. Salmon is back. Oh, random guy's back. Oh, random guy's got fans. Few Cook students. Not a bad ratio considering. Here till 6. That's unfortunate. Someone loves CS. I love this. Comp is fun, yes. Someone just wants me to say asterisk. No, that was not right. Asterisk. You know, you can always judge whether you're the most dehydrated person if you can do a whole flight without drinking. Like, let's say just even to, like, America, 14 hours. Can you do that? Not a challenge, by the way. You should probably stay hydrated. See, who wants to go to the bathroom on a flight? It's more reason to dehydrate. No, it's not. You should never dehydrate yourself. This is very bad advice. Yeah, flight bathrooms. There. All right, let's do it. No singing. No singing allowed. This is not a happy occasion. Was that Sherlock Holmes? I feel someone watched my lecture from last year. All right, let's do it. Ha 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 ha. This is just to see who was there. Who came to the lecture? This is a fast one. This might explain the other poll results. Oh, I'm impressed. It's always the same people. All right, good chat. Next one. Salmon was clearly the fastest to pick. Maybe yes. Oh, did I not press next? Okay, here we go. It's not an asterisk. It's not a star, is it? Thanks, Bree. Yay! And I know that you were just trolling me when you said asterisk. Asterisk. Let's see who's the winner. Oh, Salmon. Not even letting random guy in. Ooh. Okay, so remember I kept saying, okay, it's got to have the pointer to the next node. So that's memory address of the next node. That's what makes it a linked list, the fact that it has the next link. Oh, cannot be dethroned over here. CS is cooked. No, not at all. It's only lightly fried. Come on, this quiz is not it's not a cooking quiz, this one. This one is light. $50-50 chance over here. So remember, you do have to go through all the other elements. Yeah, we only know where the first node is, and then we only ever know where the one afterwards is. So if we want the third element, we're going to need to go to the first, the second, until we get to the third. Look, the CS is cooked is now going to come on top, and that would be very interesting. Okay, next, second last one. Well, we're just talking about a single link list, one way, into the forward direction. Yes! So much success, well done. So you just have your pointer and then you have the stab arrow, because this means dereference and go to. So it's the dereference and the dot all together, okay? So this is going to be your best friend, this arrow, for the next 4 weeks, 5 weeks, 6 weeks if you include the exam. It will be your best friend. Last question. Salmon. Too slow, too slow. See who's listening and who's tuning me out. By the way, I was the queen of tuning out when I was at uni, so I can't even blame you. Ooh, very nice. Okay, when a fixed size and structure is desired, that's not a linked list. Okay, if we know a fixed size, we go to arrays or another data type. And when elements need to be accessed randomly, you cannot do that in a linked list. Remember, in a linked list, you have to start at the start and you have to go through every single one to get to the one that you want. Whereas in an array, it's random index, so you can go to wherever you want, whenever you want. Yeah. So it's when you want to have efficient memory usage, and that's because you're not wasting any, because you're dynamically allocating memory when you need it, and also when you need to frequently insert and delete things from the list. Yeah. All right, let's see who's the winners. Number 3 is, aha! Number 2 is Salmon, knocked off on the last bit. Number 1, Alan. I don't know if anyone's watched those. They used to have these, no, you know what? I'm not going to. No, I will. They used to have these National Geographic, and it was like the birds, and there was Alan. That's what it reminds me of. This was such a tangent. I shouldn't have gone on that tangent. Okay, let's leave. Well done, Alan. Good for you. Well done, Salmon. Good for you. Good job, everyone. Good job. Okay, back to our amazing code and drawing. I'll move myself back to this side and we're back. Okay, excellent. I was the meerkats. I was like, the birds was the daytime, nighttime. That was the funniest thing also. Okay. Anyway, that was clearly a tangent. So we're going to now, we're now going to insert anywhere in the list. So we're going to specify a position and insert at that position, okay? Okie dokie. Perfect timing. And then next week we can do deletions. Okay, so now I want a function. This is the most random. Don't ever comment like this in your code. This is really just lecture vibes. Do better coding. And what I said before, I over comment in lectures because I want you to go back to this code and learn from it and know what it's doing, as opposed to I'm writing code for a specific purpose for a specific program. So I want a function now that will insert a node at a specified position in the linked list. Okay, what will I need to give this function, and what will this function give me back? What will this function return, and what will I give this function as input? What are we thinking? This delay is killing me. Node. A node is involved somewhere, absolutely. So I want to insert it at a specified position. So if I'm specifying a position, I will probably need to give it the position where I wanted to insert it. Okay, that's definitely one. The output is the head. I agree. I'm going to output the head of the list, and you're going to see this very often in linked list functions. You will mostly output the head of the list because you want to be able to traverse that list again. Okay, just 2 people participating in this decision-making process. Let's have a few more. What do you reckon? So I'm going to insert a node. So you said node. I guess that is correct. So I'm going to give it some data to make a node with that I'm going to insert. And what else do I need to give it? Yes, well done. Is head the input as well? It is, because I need to know where this linked list is that I need to insert into, right? So I'm going to give it 3 things. I'm going to give it the position where I'm going to insert. I'm going to give it the data that I'm going to insert. And I'm going to give it the head of the linked list that I want to insert into. And for my output, I will output the head of the list, just in case the insertion was at the head of the list, which means that the head of the list will change. Yeah? So this is where we're now going to have to consider those little edge cases, and we're going to have to think about what happens if I'm going to be inserting at the head, or what happens if I'm going to be inserting at the tail, blah, 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 blah. Okay. So let's just do our first bit. So struct node, and no, that's what am I doing? I'm not starting name of the function, insert at position, and I'm going to give it some data. I'm going to give it the position, and I'm going to give it the head of the list to insert into. And what we said again, I'm going to return the head. We might change that, so just hold that thought, but we might not. Okay, so we're gonna talk about that. Okay, so this is where I want us to now think about the random things that could happen. Okay, so anytime you insert into a list, think about inserting at the head of the list. This means the head will change. So that means the address of the head will change. Yeah? Inserting into an empty list. Again, this means that that node will become the head, and head will change again. Okay, so to start with, let's create our node. Okay, so we've got everything going. Let's create this node, and we now know how to do that. We've done it a few times. So we're going to do a struct node. We're going to do a pointer to a new node, and then we're going to call our function because we now don't need to do anything else. We've done it. So we're going to create the node, and we're going to create it with the data. So this data that was sent to it, and we're just going to give it null. We're just going to create a blank node. The null means it's not connected to anything. It's just hanging on its own somewhere in memory, okay? Okay, so the node has been created. Let's go first case now, okay? And the position is at the head of the list. Yep. Doesn't feel like, I don't know what's going on. Why does it become the head? Which one? In the first case or the second case? In the second case, because if it's an empty list and you insert a node into an empty list, it's the only node in there, and that means it's the head of the list. This delay is killing me. I wonder how long it is. Okay, so what happens if it's at the head of the list, okay? That means if my position, which is this variable that I've sent over here, okay? So if that position is given and that position is, I don't know, 0, yeah? Which means insert at the head of the list, insert before any, yeah, an empty list is just head is equal to null, right? There's nothing in it, yeah. And it's a perfectly valid thing to return as long as you then don't access it. Okay, so if position is 0, okay, that's the first one. That means I'm inserting at the head of the list. So I've inserted at the very top spot. What about the second case where it still will become, you know, so position is 0 and the list is empty. So that means the head is equal to null, as you said before, which means it's empty. Okay. So if I have to insert at the head and the head is null, which means that that list is empty, there's nothing in it, that means that my head is going to be the new node. Okay. So whatever node I've created here, whatever variable is sitting in here, is now going to go, I've sent it the head, which means it's got access to the head of the list, and it's going to assign that new node address to the head of the list, okay? And that means I'm done, right? It's just one node, it's inserted, and that means I can return the head and move on with my life, okay? Yeah? Maybe? Okay. So this case over here is what happens if the position is at the head of the list and the list is empty. Okay, so it means there was nothing to insert. Now the other case, what happens if the position is at the head of the list and the list is not empty? Okay, so that means I've got something in the list. It's not empty, but I want to insert at the head. So if my position is 0, but the list is not empty, so the head is not null. So it means there is something happening in this list. What would be the condition then? So that would mean I have like 751, for example, and I want to insert before the 7. So what do you think I will reassign? Where will the new node go? Where will anything go? Should I draw it up? I think we should draw it up. Why not? Yeah? So let's say we've centered a list, and this list has, oh my gosh, my pen stopped working. Here we go, we're back. Let's say my list now has 7, 5, 1, null. Okay, so I've got my list over here, okay? And let's say on this line over here, struct new node, create node, I've created a new node, and let's say that node is number 3, okay? And I've said I want to insert it at the head of the list, which means I want to insert it over here. I want this to become the head, and I want to connect it up to whatever was the head of the list. Yeah, does that make sense? So this is my new node, and this is the head of the list right now. What I want to do is I want to make this new node the head of the list, and the new node is pointing to it, okay? So the way I'm going to do it is I can't say, over here I've said, okay, head is equal to new node, okay? And that means I'm now saying the head is equal to, so this is now the head. Why can't I do that if I do it on a diagram? What do you reckon? Why would I need to do something before that? What do we reckon? Yeah, that's right. I've lost the previous head. I've got no way to hook up these two links now. There is no way to link them because I lost where I was in the list, okay? So before I do that, before I assign this head is equal to new node, I need to modify my new node. So my new node over here, I need to draw the link first from the new node to the head before I reassign them. So the first thing I'm going to do is I'm going to take this new node, I'm going to access its next pointer, and I'm going to assign the head to it. And what that does is it creates this link over here. So it allows me to go new node next. I've gone in here and I've pointed it to the head. And now what I'm going to do is I'm going to reassign the head because this is no longer the head. This is the head now. So now I'm going to say the new head is going to be the new node, and I'm going to return the head. So this list would now be 3751, and I've got it. Yeah? How is that? We'll run through the code as well, don't worry. So those are two kind of like off conditions perhaps that, you know, might happen. So inserting at the head. Let's see what happens if we just want to insert it, right? Should we just insert the whole, let's just insert it anywhere, right? At position is equal to whatever. So we're going to loop until we get to the position just before where we want to insert a node. Okay, so I've got my new node. I've got 2 edge cases covered. Great. So if I'm going to traverse a linked list, okay, I'm going to create a current node where I'm going to keep track of where I am because I don't want to lose that head. So what I'm going to do here is I'm going to create a current variable, and I'm going to place the address that head had in it, and I'm going to use that for my traversal and for movement. Okay, if I'm going to count up my nodes and then I want to insert the node, what else do I need if I'm going to count my nodes for position number? What do we reckon? What do I need? When it's silent, I always feel like I've lost everyone. I need something to count. I need a loop. I need a counter, sorry, not a loop. So before I start, I need some sort of counter that will count off node for me so that I know that I've reached the position. So if I say I want to insert at position 2, okay, that means my list is, so let's draw it out so we can see this problem in a diagram. Okay, so I don't know what I just, here, you can't actually see that. Here we go. So let's say we have a list, and that list is okay, and I want to insert at position 3. Okay, so if I want to insert at position 3, that means I've got to go, okay, this is node 1, this is node 2, this is node 3. If I want to insert at this third position, I want to stop on this node because I want to be able to make the connection. If I stop on the third node, I no longer know where that previous node is, right? So what that means is I will not be able to connect it up, okay? I want this node here to become the fourth node. So this one needs to become the fourth node. This is going to become my third node, whatever it is. Okay, so that means I want to start my counter at 1, as someone said. Okay, so I'll start my counter at 1, and I want to stop just before the node where I want to actually get in to the list. Okay, let's have a look. Yeah, a linked list is a one-way street. In this, you can only go in one direction in our case, just forward, right? You cannot go backwards. Okay, excellent. Yes, you will need to check that position exists, but we will talk about that in a second. We will take care of that, right? Because what happens if that position is not found? That's a good edge case as well. Okay, great. So we've got our counter to count our nodes. So now we need some sort of loop to move through the positions, okay? So first of all, we need to move through the nodes, okay? So there's going to be some sort of current is not equal to null. That means we visit every node, and we can discuss this, right? Sometimes you need to stop at the previous one. We will discuss why we're doing current not equal to null. When we run through the code, you'll see why that is. We're going all the way to the end of the list. And also, a really good thing to do after you leave this lecture is to take this code and go home and try doing whilst current next is not equal to null, or whilst current is equal to null if we ran out of time, to see what it actually does, okay? And to see what happens, and then run through it with a diagram yourself to be able to understand why certain things happen in the list. Okay, so basically what I want to be doing is I want to be moving through the list, and I want to be moving through it until my counter is not equal to the position, okay? So until this counter that I've just created is not equal to the position that I was given, I'm going to keep moving through this list. Okay, so to move through the list, I'm going to current is equal to current next, which moves my nodes along. And what else do I need to do? I need to increase my counter each time, because if I've moved up a node, I need to increase my node count as well. Yeah? So that means that when I exit this loop, okay, one of two things might be true. Either current is equal to null, which is this condition over here has been met. So current is equal to null, and that means we have reached the end of the list. Or the second thing is true, right? Which is counter is equal to the position, which means that we have gotten to the position to insert. Okay, so if there's two potential things, okay, so I'm going to check that it's the thing that I want it to be before I insert. So what I'm going to do is I'm going to say, okay, if counter is equal to position, so if I exited that while loop for this reason, then I'm going to do my insertion, okay? And I'm going to return the head of the list. Okay. So to insert the nodes, okay, I have this new node over here that's been created. And let's say I'm currently sitting at this node over here. So this is my current node. And I want to insert it in this direction. So I want my current node to point to the new node and my new node to point to the next node. Yeah? So which connection do you think I would need to make first? So if I say my current next is going to be new node, what will happen is I'm going to lose the location of the next node. I'm going to just drop off this part of the list and I'm going to lose it, right? So I can't do that first. So the first connection I need to make is I need to make this connection over here. I need to connect my new node into the one that is next, okay? So in code, that's going to be my new node next, because I'm connecting the next node from my new node. I want it to be the current next, okay? Because remember, I'm currently sitting over here, and that means whatever is inside here is the address of this node. And I want this new node to have this next address. Okay, so now I've hooked this up. What I want to do is I want my current next to point to the new node. So I want this connection now to happen. Okay, so my current next now, I want it to point to the address of the new node. Okay, so now I've got these two connections happening. And what it means is this node is now inserted and this link is now gone, okay? So the connection goes like that now. And then I return the head of the list. Now, if I have reached the end of the list over here, which means that it's equal to null, right? So in this case, the current is equal to null. I've reached the end of the list and the counter has never equaled the position number. That means something was wrong with that position number, right? So there was not enough elements in the list, or the counter was too big, right? So, you know, it could be that the position number doesn't exist, it's too big. Yeah? How is this feeling? Is this feeling, this might be feeling more nasty than before. I'm sure it is. So if we were to run it, let's just run it, and then we're going to go through the code and walk through it, and that will be the end of the cooking. Okay? Let's do it like that, and then you can see what's going on. It's always better after we run through the code. So let's do that, and let's actually call the function. Let's go insert at position, and how was it? Is it a data position? So let's do number, insert 42 at position 2 and give it the head of the list. And then let's print list with the head. So now I'm just calling the functions, okay? Okay. Let's do it. Let's compile it and let's run it. Okay, so the first, I shouldn't have left so many things in. So this is the first list, 751. Then we inserted at the tail, 75111. And then we inserted 42 at position 2, 752, 42, 111. There is a mistake. Where did there is a mistake inserted at position 3. So we made a mistake in logic somewhere, right? Which we can fix in a second. Let's run through the code and then we can see where that mistake has happened. Does that sound good? Run through the code? Yes, no, maybe? Yes. We're just going to do it. We're going to do it. It's going to happen. Okay. Inserted position 42 to and at the head. So I'm going to erase all of this so we can start again. And let's do it with the list that we have now, which is 7, 5, 1, 11, null, and we have just called our function and we have said insert at position. The node is 42. We want to insert at position 2 and we've given it the head. Okay, let's go down to the function that we're using and we're going to run through it. Okay, excellent. Okay, so the first thing we do is we go to line 110 and we say, okay, create a node for us. And the node is going to have this data in it. And it's going to be the size of a struct node, and put the address of that new node into the variable new node. Okay, so we've created this. It's going to have the data in it, which is the number 42. And we said to create it with null. So that means this is what my node looks like now. It's pointing to null. It's sitting empty. It's sitting pretty. It's not connected to anything. It's just floating in space. So I go to check the first thing. Okay, is position 2. And right now, my position, so position right now is equal to 2. Okay, because that was given to us as the function. So position is not 0. I skip through this if statement. I go to the next one. If position is equal to 0, well, position is not 0, so I'm going to skip through that. So we go right back to this one over here. Okay, and we will do next week, don't worry, we'll go through those 2 edge cases. Let's just focus on the meaty bit. Okay, great. So the first thing I do now is I declare a new variable current and I assign the value of head to it. So this was head of the list because it's where it starts, and what I've done is I've also assigned current to the same value. Okay, excellent. I then declare a variable counter and I make it equal to 1. So I've got a new variable counter and it's equal to 1. While current is not equal to null, so we check if current is it equal to null? No, it's not, because there's a node afterwards, so this is true. And so I'm going to check the next thing. Is counter not equal to position? So 1 is not equal to 2. So that is true as well. So both things are true, which means this while loop is true. And we increase the counter by 1. So the counter is going to go to 2. And my current is going to jump to the next node. Okay, so my current has moved over by 1 node. Excellent. I go back and I check again. Is current not equal to null? Well, no, it's not, because I've got a node following that node. So now let's check my counter. Is counter not equal to position? Position is 2, counter is 2. They are equal to each other, which means that this is not true, yeah? So I'm going to exit out of this loop. Okay, I'm exiting out of this loop and I'm now over here. So my next check is counter equal to position? So is 2 is equal to 2? Yes, that is true, which means I enter in here. What I do in here, I go to the right side first and I grab the next address of current. Current is over here, so I grab what is sitting next, so the address of this node over here, and then I assign it to new node next. So whatever is sitting in here is now assigned to my new node next. So let's say that this is, let's say this is just for fun, right? These are not real. The address is A, the address is B, C, D, okay? So that means the next one here is C, the next one here is B, the next one here is D, and then the next one here is null. Okay, so what this is saying is grab whatever is sitting inside this next, which is C, and assign it to new node next. So go in here, and instead of this null, I'm now going to assign the value that was sitting inside current next. So what I'm going to do is I'm assigning it the value C, which means that this node now is pointing to this one. Okay, so I've made this connection now. Okay, I've got my first connection. I now go to the next line, and it says grab the address of the new node. So wherever this new node is sitting, and let's say it's sitting at E, so new node is equal to E, where the actual node is, and then assign it to current next. So assign the value of this node, new node is equal to E, in here, which means that I now have this connection. So this is now pointing to the new node, and the new node is now pointing in here, and this connection no longer exists. Yeah? How does that feel? And then I return the head of the list. So I return this head because I don't know if I inserted at the head of the list, and I might have changed the head of the list, which is why we keep returning that head. Okay, how does that feel? Yeah, I mean, except for that it's not inserted in the right place. Yeah. Yes, it's placing it at the third position. So it's not the correct, we just have to fix the logic a little bit. But I've really run out of time, so I'm going to leave you to fix the logic of that, and then we can do it as the first thing next week. Okay, tell me how that feels. How are you all feeling? Okay, I promise you it does click, and the more you diagram, the more it clicks. Like you can see that it doesn't make any sense when you're just looking at new node next is equal to current next is equal to new node. It's madness, right? But when you draw it, you can see where the arrows should go. Okay, so always draw linked lists. Otherwise you're going to go mad. I'm going to save this as well so you can see it. And remember what I said. Go home. First of all, fix the logic. Make it insert into the right place, right? We're going to do that next week, but make sure it's inserting into the right place. And then play around. Why did I do current is not equal to null here? Do current next is not equal to null. See what that does. Try inserting at the tail. So insert at the end of the list. Try inserting at the head of the list. See that it's returning the right things, right? So always try different things. There you go. I'm going to get you to give me some feedback if you like. Let me know if the lecture was too fast, too slow, just right. I do take the feedback on board, and I make changes for the next lecture. So it's nice to know, because even if you feel like you don't want to give feedback in the lecture, it's nice to have, it's nice to be able to see that you're getting it, because it's especially in this format when I can't see you at all. Can't even see anyone napping, so I just don't know what's going on. All right, amazing. I hope you all have a great one day without an assignment, and look forward to seeing the next assignment. I promise you, I reckon link this assignment is not harder, that was Freudian slip, is easier than the arrays assignment, except for stage 4, which is not going to be that pretty. Again, so, but still fun, and you're going to learn a lot. All right, have a fantastic, fantastic time. And I look forward to seeing you next week on Monday, and have a great rest of the week. Next week is stress less week, which is really ironic, but you get to pat a llama. So, yep. All right. See you guys later.